On discovering that matter is made up of atoms, scientists' attention was shifted towards identifying the mass of atoms. Since atoms were small particles and could not be separated, scientists were not able to determine the actual mass of an atom by weighing it. It was possible to calculate the mass of an atom by weighing an element and then dividing the weight by the number of atoms. However, there was no method to count the number of atoms available in an element. In an attempt to find a solution to the problem in the 19th century, Dalton made some assumptions based on Gay-Lussac's findings. Based on Gay-Lussac's findings, Dalton assigned hydrogen a weight of 1. He used hydrogen as a standard for determining the atomic masses of other elements and published the first table of atomic masses. Note that the atomic masses in the table indicate relative mass and not the actual mass of the atoms, which means that the masses of elements is relative to the mass of hydrogen. In 1961, scientists met at the International Union of Pure and Applied Chemistry and decided to use carbon as the standard base. Carbon has 3 isotopes, C12, C13 and C14. Since C12 was found to be the most abundant, it was taken as the standard scale. By that time, due to the advancement of technology, scientists started using a mass spectrometer to calculate the accurate atomic mass of elements. The atomic mass of carbon was determined using a spectrometer and was found to be 12 atomic mass unit AMU. All other atoms were assigned a mass relative to the atomic mass unit of carbon. Thus, the atomic mass of an element is the number of times an atom of that element is heavier than an atom of carbon taken as 12. As carbon-12 is an isotope of carbon, it is represented as 12C. Therefore, one atomic mass unit is defined as a mass equal to 1/12 the mass of carbon-12 isotope. And the value of one atomic mass unit was determined to be 1.66056 multiplied by 10 raised to minus 24 gram. Let's determine the atomic mass unit of hydrogen based on this formula. We know that one atomic mass unit is equal to 1.66056 multiplied by 10 raised to minus 24 gram. The mass of a hydrogen atom was determined using a spectrometer and was found to be 1.6736 multiplied by 10 raised to minus 24 gram. Therefore, in terms of atomic mass unit, the mass of an atom of hydrogen atom is said to be 1.008 AMU. When chemists expressed atomic mass on carbon-12 scale, they named it as unified scale, and the unit was represented as U instead of AMU. Though AMU is still used in most places, chemists now use U as the unit. Hence, we can represent atomic mass of hydrogen as 1.008 or 1U, and that of oxygen as 15.9994 or 16U. We know that when atoms of the same elements possess different atomic masses, they are known as isotopes. Hence, for isotopes, the average value of the atomic masses is considered as the atomic mass unit. For example, chlorine has 2 isotopes with average atomic masses of 34.97 and 36.97 units respectively. The relative abundance of the isotopes is 0.755 and 0.245 respectively. Relative abundance refers to the abundance isotopes of an element, as naturally found on a planet. Average atomic mass of an isotope is the sum of abundance of each isotope multiplied by the precise atomic mass. Thus, the average atomic mass of chlorine is calculated as 35.46 U. Hence, the average atomic mass was redefined as the atomic mass of an element is the average relative mass of its atoms as compared with an atom of carbon-12 taken as 12 U. We can also calculate the average atomic mass using fractional abundances of isotopes of an element. Fractional abundance of an isotope is the fraction of total number of atoms that is comprised of that particular isotope. The formula for calculating an average atomic mass from fractional abundance is fractional abundance multiplied by atomic mass of that fraction. Thus, the average atomic mass will be the sum of the products of fractional abundance of the isotopes and their corresponding mass numbers. For example, neon consists of 3 isotopes: neon 20, neon 21 and neon 22, which have mass numbers and fractional abundances as shown in the table. The average atomic mass of neon will be calculated 20.179 U. When the atomic mass of an element is expressed in grams, it is called gram atomic mass. Gram atomic mass is also called 1 gram atom of the element. For example, 1 gram of magnesium is equal to its atomic mass expressed in gram, which is 24 gram. Like atoms, molecules are also very small. Hence, their mass cannot be determined by weighing them. Therefore, the molecular mass is determined relative to the mass of carbon atom taken as 12 U. The molecular mass of substance, element or compound is the number of times the molecule of the substance is heavier than 1/12 the mass of an atom of carbon-12. In other words, we can say that the molecular mass of a substance is the average relative mass of its molecules as compared with the mass of an atom of carbon-12 isotope taken as 12 U. The molecular mass of any element or compound can be calculated by adding the atomic mass of all the atoms present in one molecule of that element or compound. For example, the molecular mass of water will be the atomic mass of 2 atoms of hydrogen plus the atomic mass of 1 atom of oxygen, which is 18.02 U. When the molecular mass is expressed in grams, it is known as gram molecular mass. Gram molecular mass is also called 1 gram molecule of the substance. For example, 1 gram molecule of water is 18 grams. Lastly, let us look at ionic compounds. Ionic compounds such as sodium chloride or potassium nitrate do not contain discrete molecules as their constituent unit. The ions in such compounds are closely packed in a 3-dimensional structure. For example, in the sodium chloride crystal, an ionic bond is formed between a sodium ion and a chloride ion. However, in its crystalline form, each sodium ion is surrounded by 6 chloride ions. So, we have to calculate the formula mass instead of the molecular mass. Formula mass is the sum of atomic masses of atoms present in one formula unit. Thus, the formula mass of sodium chloride is the atomic mass of sodium plus the atomic mass of chlorine, which is 58.5 U. When the formula mass is expressed in grams, it is known as gram formula mass. Before we begin, let's step into a store to buy some apples. Let's say we need 24 apples. When we collect them, we get them in 2 boxes, with 1 dozen or 12 apples in each box. Here, dozen is a unit of measurement that helps us simplify and state a large quantity, like 12. When scientists were working with elements and compounds, they felt the need to have a unit of measurement to count entities at the microscopic level. Thus, the SI base unit, mole, was introduced. Mole is the amount of substance which contains as many elementary entities as there are in 12 grams of carbon. Elementary entities may be atoms, molecules, ions, electrons, or protons. Note that 1 mole of a substance always contains the same number of entities, irrespective of the identity and kind of the substance. The term mole is used to count particles such as atoms, molecules, ions, electrons, and protons. Hence, we must indicate the nature of the particle under observation. For example, saying 1 mole of hydrogen would be incorrect. We need to specify the entity we are referring to. That is, hydrogen atoms or hydrogen molecules. Thus, the correct term would be 1 mole of hydrogen atoms or 1 mole of hydrogen molecules. But what is the value of a mole? Let's find out. We know that a carbon-12 atom is used as a base to calculate the atomic mass of elements. Hence, scientists used carbon as the base to determine the value of 1 mole. They used a mass spectrometer to determine the mass of a carbon-12 atom and found it to be 1.992648 multiplied by 10 raised to minus 23 gram. They then divided 12 gram moles of carbon-12 by the mass of carbon-12 and obtained 6.0221367 multiplied by 10 raised to 23, which is the number of atoms in 1 mole or 12 gram of carbon. This is the value of 1 mole and is known as Avogadro's number or Avogadro's constant, in the honor of Amedeo Avogadro, and is usually represented as Na. Avogadro's number or Avogadro's constant is defined as the number of elementary entities, atoms or molecules or ions in 1 mole of a substance. Thus, we can say that 1 mole of water molecules contains 6.022 multiplied by 10 raised to 23 water molecules. Having found the number of moles in a substance, we can determine the mass of a mole, also known as molar mass. Molar mass is the mass of 1 mole of substance expressed in grams. The molar mass is numerically equivalent to the atomic or molecular or formula mass in U. Let's determine the molar mass of water. We know that water comprises 2 hydrogen atoms and 1 oxygen atom. We can obtain the atomic masses of hydrogen and oxygen from the periodic table. The atomic mass of hydrogen is 1.00794 and the atomic mass of oxygen is 15.9994. If we add the atomic masses of 2 hydrogen atoms and 1 oxygen atom, we get the molar mass of water as 18.02 gram. We've learnt that molecular mass of a substance can be obtained by adding the atomic masses of all the atoms present in one molecule of the substance. And the molar mass is numerically equivalent to the atomic or molecular or formular mass in U. Thus, we can conclude that the mass of 1 mole of any substance is equal to its molecular mass. We have seen how to determine the number of entities present in a substance. At times, scientists also require to know the percentage of elements present in a compound. This information helps to determine the purity of the chemical compound under observation. The percentage composition of elements or constituent in a compound is the number of parts by mass of that element or constituent present in 100 parts by molar mass of the compound. Let's look at an example. We know that the molar mass of water is 18.02 grams. Based on this, we can calculate the percentage of hydrogen and oxygen as shown. Thus, the percentage of oxygen and hydrogen in water is 88.79 and 11.18 respectively. Molar mass and percentage composition helps us understand the quantitative data associated with a chemical compound. But how does one arrive at the chemical formula of a compound? In other words, how did scientists obtain the formula H2O? The chemical formula of a compound is derived from 2 parts, the empirical formula and the molecular formula. The empirical formula is defined as the formula which gives the simplest whole number ratio of the different atoms present in one molecule of the compound. For example, the empirical formula of water is H2O. This indicates that in water, 2 hydrogen atoms are present for each oxygen atom. Similarly, the empirical formula of glucose is CH2O. This indicates that there is 1 carbon atom for every 2 hydrogen and 1 oxygen atoms. Note that the empirical formula only indicates the atomic ratio of the elements present in one molecule of the compound. Now, let's look at molecular formula. The molecular formula is defined as the formula which gives the actual number of atoms of various elements present in one molecule of a compound. In case of water, the molecular formula is H2O, same as the empirical formula, because one molecule of water contains 2 atoms of hydrogen and 1 atom of oxygen. In case of glucose, the molecular formula is C6H12O6. This means that one molecule of glucose has 6 carbon atoms, 12 hydrogen atoms and 6 oxygen atoms. The molecular formula of a compound is an integral multiple of the empirical formula. The equation can be illustrated as shown. The value of N can be obtained by dividing the molecular mass with the empirical formula mass. The empirical formula mass is the sum of the atomic masses of the atoms present in the element. Let's say we have a compound CH2. The empirical formula of the compound will be the sum of the atomic masses of one carbon atom and two hydrogen atoms, which is 14 gram-mole. Now, let's say that we know the molecular mass of the compound is 28 gram-mole. Thus, 28 divided by 14 gives us 2. Then, we multiply 2 by the empirical formula and get C2H4. We've learnt how to calculate molar mass, percentage composition, empirical formula and molecular formula. But when do we apply these calculations in chemistry? Let's say we have conducted an experiment and obtained a compound that has 29.11% sodium, 40.51% sulfur, and 30.38% oxygen. And the molar mass of the compound is 158.1 gram. How can we determine the empirical and molecular formula of this compound? First, we have to convert the mass percent to gram. As we have the values in mass percent, we can consider the value of the sample as 100 gram and then convert the percent values to gram. Next, we have to determine the number of moles in each element. Divide the mass of element in gram with the atomic mass of the element. The atomic masses of various elements can be identified from the periodic table. Therefore, the relative atomic mass of sodium, sulfur, and oxygen are 23, 32.1, and 16 respectively. On substituting the values in the equation, we get the number of moles for each element as 1.266 and 1.897. Next, calculate the simplest molar ratio. Divide the moles of various elements present in the compound by the smallest quotient obtained as a result. This gives the simplest molar ratio as 1:1:1.5. If the ratios are not whole numbers, then multiply the number with suitable integer to convert them into whole numbers. In this case, if we multiply all values by 2, we get all ratios as whole numbers. That is, 2:2:3. Write the empirical formula by mentioning the numbers after writing the symbols of respective elements. First, write the element symbols next to each other. Then, insert the obtained numerical value of the simplest whole number ratio at the lower right-hand corner of each symbol. This gives the empirical formula of the compound. That is, Na2S2O3. Now, let's see the steps to determine the molecular formula. First, calculate the empirical formula mass. The empirical formula mass can be obtained by adding the atomic masses of all the atoms present in the empirical formula, which is 158.1 gram. Now, divide the molar mass by the empirical formula mass to identify the value of N, which we get as 1. Then, molecular formula of a compound can be determined by multiplying empirical formula of the compound with N. In this case, the molecular formula will be the same as the empirical formula. That is, Na2, S2, O3.